let's take a deep dive into the Edith Cowan University car all the way from Australia. Fascinating technical entry, really different with their live rear axle and the engine mounted almost like it's on a scooter, and some clever XF1 style ways of making the carbon fibre chassis. So with this car I want to start at the back because it's quite different from anything else we've already seen. Normally when we look at the back of the cars you see a space frame, you see double wishbone suspension, quite different here. So Brock, just very simply explain to me this kind of the concept of what the rear end of this car is.
Yeah, so the rear end of this car is effectively, we built it sort of around this sprint axle here. It's the second time that we've run this sprint axle in our car before. We were running a Watts linkage on the previous car, but because the axle and the engine were independent of each other, the chain length, we kept it fairly long to reduce the effect of the binding roll. So this year we're looking to tighten that chain up, reduce the weight in that, push the centre of gravity backwards a bit, and also push some of the aerodynamic, like the front wing components forward. So that was where it started. We were sort of drawing up solutions, manually sketching them around, and we sort of realised that the suspension members were in the perfect position to mount the engine. So that was another part of integration for this concept. It took a few weeks to develop that and just get it around just what it was and what it was going to be. And then several more months of further concept development and design in that way. So we're actually really looking to reduce the parts count, increase the simplicity on this. So this suspension system effectively is about a third the parts of a typical AA-arm pushrod suspension system. We've also run Dion beams in the past, and this is probably about half that in terms of parts count too. So it's really low on that parts count, less components to fail, less parts to make as well. So we wanted to maximise our testing time as an overall goal. But yeah, that's pretty much where it started, I'd say.
Okay, so from a driver's point of view, how does this feel different in terms of compliance when you're on the circuit?
In terms of compliance, it's actually a fairly stiff system. So we were lucky enough to go to Multimatic to do a hub-to-hub torsional test. We've done a hub-to-hub on our previous space frame car, and we were looking at, I think, 950 newton meters per degree Antec for the space frame car. This car is roughly double that on a hub-to-hub test. And now the chassis itself is also roughly, I think, 3,700 newton meters per degree in terms of stiffness. So the overall compliance of this system, and even the front as well, is quite low. So the drivers love this car. They love driving it. It's meant to sort of handle a bit like a go-kart. We wanted to have that aspect in, and a few of our drivers are also sort of ex-go-kart. Not anything high level, just sort of grassroots stuff, but they love it.
Yeah. Oh, it's a bold choice. It seems to have worked out for you.
Yeah.
Next, I want to have a chat about the engine, which again, this is a combustion engine. We're going to see a lot of electric cars on this, so we'll have a look at that next. So looking at the engine, Cian, there's not much of an engine here, a little single-cylinder engine.
Yeah.
Tell us about the engine choice and about its mounting.
Yeah, sure. So essentially, in 2022, we made the switch to single-cylinder engines. It was a cost choice coming out of the COVID situation. Essentially, we started off with KTM 450, and in 23 we switched to this Yamaha YZ450F, and there's some really cool details about this off-the-shelf engine. We haven't opened the thing up, but one of the cool things is the flipped head arrangement. So most dirt bike engines will have the exhaust coming out the other side and the intake on this side. And FS engines, you want that swapped around. So we have this really nice straight runner exhaust right at the back, and it helps a lot with thermal management around the engine bay. It also has an integrated dry sump, so that's something that we don't have to build outside. It's another thing that we've been able to make simpler overall. And the engine itself is unsprung within this integrated powertrain suspension system, which Antec can speak to a little bit.
Yeah, so the engine being unsprung is quite unusual. However, we find that the engine adds rigidity to the overall frame, as so does the axle. And in reality, if you compare something to like a in-hub electric car, the unsprung mass the difference isn't as high as you think. So overall, dynamically, the car performs very well. The suspension is kinematically over-constrained in roll. As you can see by the model here. In roll, these two side links have to either extend or compress. However, in heave, we are perfectly kinematically free. And we find that for a 50 mil wheel travel, the side links only need a change in length by about 0.2 millimeters. And we find that the compliance in the sphericals and things like that are more than adequate to actually supply free movement in roll, while supplying a lot of lateral rigidity.
Okay.
Yeah. If I can speak to the drivability of it as well a little bit. So when we switched in 22 to single, it's also when we switched to the micro sprint rear axle, which is the solid axle integration of a spool and a Dion beam. However, at that point, the engine was still sprung, the axle was unsprung, so we were getting some chain misalignment and issues and that kind of thing. An ancillary effect of having that is that it's delayed the jacking motion that we try and get in the car a little bit, so it's made the jacking more predictable and more controllable. So the car still rotates as well as it did in 22, but it's so much more controllable the way it rotates. So that's been a really cool ancillary effect of having an unsprung engine.
Okay. Moving on from another aspect of the engine. So your engine goes up and down what I'd call in a scooter style.
Yeah.
With everything on the rear end. You've got some radiators here for cooling that are mounted to the chassis. So tell us about the cooling package and tell us how you're sure that you aren't going to have hoses fraying from the up and down motion.
Yeah. So essentially, the cooling package uses the two stock radiators. We did a lot of simulation work to make sure that they would actually work in an FS application. We developed a transient endurance simulation using an Excel spreadsheet that covers 30,000 points of data. But in terms of the motion of it all, you can see that on the radiators themselves, we've modified them by welding aluminium tubing to make sure that that part moves as little as possible, and with the introduced areas at the moment using the rubber lines. So if we actually were to twist this a little bit, the lines will be a bit hot, but you can see there's flexibility in the way the line moves. So, and we've also mounted GoPros in the past from here to actually look at that movement. So we're making sure that we are not having that heat shield hit the exhaust runner or hitting the chain mount. So overall, the system can actually move quite a lot. Like, there's a lot of movement in it. So we've introduced that to allow the whole system to make sure that it doesn't actually start degrading or start wearing out the aluminium tubes. You can see as well, this is another thing that we've done on this side. We have a line mount for the hard line, and that's just to ensure that that's not moving and fatiguing the weld.
Yeah, excellent. So that's the rear end. Let's move now to the front of the car. So now we come around to the front of the car, and first of all, I want to talk about the carbon fibre monocoque, because it is slightly different to other carbon tubs that we see here.
Absolutely. So the chassis is not a typical molded chassis. The team is quite concerned with resource expenditure, and effectively the resource involved in creating a plug, laminating molds off of that, laminating the chassis, and then doing the final prep, to us just outweighed the performance benefits you get out of a molded monocoque. So instead what we've done is we've done what we call a cut and fold, very similar to old school F1 chassis, whereby we make a flat panel of carbon and aluminium honeycomb composite. We will then, in CAD, purposely design the structures can be flattened as a sheet metal structure, and we can then CNC route this shape, put in the bend lines, and then fold it up like an origami structure. So for example, on the front you'll see there's a fold line around here. We'll basically laminate that over, reinforce the structure, and then the whole chassis is about 3 sections, so front, mid, and rear. These all get laminated at the joints with a skin equivalent layout.
Wow. Okay, so you've then got your bulk structure, but obviously there's a lot of safety factors and other things that need to be bonded into this. So, Brock, do you want to talk us through what's involved with that?
Yeah, can do. So by the rules, there's several safety devices that you need to have, one of which being the impact attenuator. So basically it's in the front of the nose cone. You can't quite see it at the moment, but it can be a few different constructions. So you can get a standard foam one, or you can fabricate one yourself. We chose to fabricate one ourselves, just it's better for us for packaging. But that also means that we need to test it. We have a testing rig basically back home where we take the impact attenuator and we put that and a 50mm section of the front of half of the chassis, and we crush it and effectively measure the energy absorbed and the total deflection, and then check with the rules, make sure it's safe or, you know, for use. So there's a bit of testing involved with that, destructive testing, which, you know, is quite nice. Everybody likes a bit of destructive testing. Also put a bit of work this year into the harness attachment points as well. So just, again, that's another SES requirement, making sure the drivers are safe, and effectively pretty simple design with the U-bolts, I would say. It's just basically a long rod that we bent around and then bolted to the honeycomb itself. Yeah, quite simple, and the layout's quite not too hard to do. So really, yeah, just keeping it all simple. Really the goal.
Moving on now to the front hubs, which you'll see obviously with the front wheel and the front suspension. You've gone quite different with the design. I mean, obviously, I think everyone thinks of these as mini F1 cars, but you don't have 2-second pit stops, so you've got quite different wheel design integrated into the hub. Tell us about that.
Yeah, so we've been running basically a wheel and hub integrated part for a number of years now. Basically, again, looking at parts elimination and reduction. So not just the rear end, that's not also the only focus in that regard. So that front, we call it a WUB, so wheel hub, which is a fairly normal term for us now, but is strange out of context. Yeah. So the front WUB is also not just the wheel and hub, it's also the mount for our brake calipers, so it removes the need for brake bobbins, and it also mounts our chopper wheel, which our Belleville tensioning system for our bearings mounts into as well. So really, yeah, just again targeting the number of parts that we can reduce.
Okay, nice bit of design. And then finally, front wing, in terms of structure and aerodynamics, it was quite sophisticated.
Yeah, on the surface it may appear to be, but it's all about design for manufacturing. We have a small team of about 15 people, so we need to be able to turn these cars around in a year. So for example, the front wing main plane, it's hollow, as you can see, and all that is a few skins of carbon fiber with some marine plywood ribs for reinforcement. The main skin is produced not with tooling board, not with a crazy a carbon fiber mold or anything like that. It's simple MDF that we routed out into a plug, and then we wet lay up carbon fiber over that plug, and that produces the skin. The end plates, as you notice, are quite unique. We've used quite a lot of additive manufacturing. So this is FDM printed out of solid PETG filament. And in that, there's some unique opportunities with that. You can add your corner radiuses for everything. By rules, you need to have a 3mm radius on all front leading surfaces to not injure passers-by or anything like that. So that can get immediately put into the design. Other funky shapes, such as this canard with a bit of extra curvature, can be added in with very little complexity to the actual print time as well. Something like this can get turned around in about 12 hours on the printer. Meanwhile, a composite equivalent would take weeks of work to get done. And as you can tell, it's reasonably structural. It may not survive a cone strike, but then again, a composite one may not either.
Yeah, fantastic. Well, front to rear, really interesting car. Thanks for taking us through it. And, well, best of luck in the competition.
Thank you very much.